Good morning, FLOPS. I'm Lindsey Kuper. I'm an assistant professor at UC Santa Cruz. Thank you very much to Atsushi and Michael and to the entire FLOPS organizing team for inviting me to speak at FLOPS and for their great work organizing this event. On a personal note, FLOPS was the very first conference that I ever had a paper rejected from, way back in 2010 as a new grad student, so I feel particularly honored to have been asked to give this talk today. My talk will be about something that I've been very excited about recently, which is the potential of using modern language-integrated verification tools to help us build distributed systems that are guaranteed to work like they're supposed to, and for those guarantees to apply not just to models, but to real running code. In the beginning part of this talk, I'll explain what I mean by distributed systems and what kinds of specific challenges they present. Then, I'll briefly introduce the Liquid Haskell language integrated verification system. And finally, adventures. I'll share some highlights of two projects in this space that my students and collaborators and I have been working on. So let's start by talking about distributed systems. Imagine some number of independent machines that communicate by passing messages to one another over a network. They could be close or far apart, but we're especially interested in so-called geo-distributed systems where that network may span the whole planet. For example, the nodes in this graph roughly correspond to the locations of some of Amazon's data centers, and it's at this larger planet scale that some of the most interesting and challenging issues arise. Many of those issues have to do with failure and the need to keep operating in the presence of partial failure of a system. Amazon had a very colorful description of this in their SOSP 2007 paper on the Dynamo data storage system. Customers should be able, they wrote, to add items to their shopping carts even if disks are failing, network routes are flapping, or data centers are being destroyed by tornadoes. I happen to be from Iowa in the Midwestern United States, so tornadoes were very real to me growing up, but feel free to substitute any natural disaster of your choosing. So not only can network connections fail, but nodes in this network can fail as well, due to tornadoes or whatever other reason. And it's important for the system to continue to operate and respond to requests even during a failure, because, in the pithy words of Werner Vogels, everything fails all the time. So this problem of partial failure and needing to continue to operate in the presence of partial failure is in many ways the defining characteristic of distributed systems. But in geo-distributed systems, we have another fundamental problem, which is that the speed of light is slow. This is a bundle of pieces of wire, each about 30 centimeters long. Grace Hopper famously distributed these at her lectures to demonstrate the distance that an electrical signal can travel in 1 nanosecond. These were some of the actual pieces of wire that she handed out, and they're at a museum now. So the speed of light is slow. It only goes about 30 centimeters in a nanosecond, or as my friend May Milano puts it, it's only about 4 inches per clock cycle. So if we're talking about machines that might be on the opposite side of the world from each other, that's a lot of clock cycles that can go by between when a message is sent and when it arrives, even under ideal conditions. So, whether we're talking about failure, disks failing, cosmic rays, network cables being taken out by backhoes, data centers being taken out by tornadoes, or just the more mundane but unavoidable issue of long latency between machines that are far apart, one way to mitigate these challenges is to have data that's replicated across a number of physical locations. This helps ensure the availability of data. In other words, it helps ensure that every request gets a meaningful response. So if I have data that I both don't want to lose and that I want to make sure remains available for requesters, whether it's baby pictures of my daughter or any other data that I may care about, I'm going to store multiple replicas of that data, both within data centers and across different data centers. This is done for reasons of, again, fault tolerance. The more copies you have, the less likely it is that you'll lose the data, as well as data locality to minimize latency. We want a copy of the data to be close to whoever's trying to access it, whether they're in Kyoto or Santa Cruz, and reasons of throughput too. If you have multiple copies of data, then in principle, you can serve more clients who are trying to simultaneously access it. But while having multiple copies is essential for all these reasons, it introduces the new problem of having to keep those replicas consistent with each other, particularly in a network where we can have arbitrarily long latency between replicas due to network partitions. So as I tell the undergrads who take my distributed systems course, replication is both the cause of and the solution to most distributed systems problems. We have to replicate data, but then we have to keep those replicas consistent with one another. Now we know that trying to keep geodistributed replicas perfectly consistent at all times is a fool's errand. A classic impossibility result tells us that the only way to accomplish perfect consistency in the presence of network partitions is to compromise on the availability of our data. And since network partitions are inevitable when working with geodistributed data, we often choose to design systems in ways that permit clients to observe certain kinds of disagreement among replicas in the interest of prioritizing availability. If we are going to allow certain kinds of disagreement among replicas, we need a way of specifying a policy that tells us in what ways replicas are allowed to disagree, under what circumstances they're allowed to disagree, and under what circumstances they must agree. Let's look at a couple examples of those policies and some ways in which they can be violated. One of the properties of interest is called strong convergence. This says that if replicas have received the same set of updates in any order, then those replicas have equivalent state. For instance, let's say that my partner and I are both updating our shared photo album of pictures of our daughter called Photos. I add one photo, which makes it first to replica 1 and a little while later to replica 2. Meanwhile, my partner adds a different photo, which makes it first to replica 2 and later to replica 1. Although the replicas receive the updates in opposite orders, their states agree at the end. So this execution enjoys the property of strong convergence. In this example, it's pretty obvious that this is the case because our replicated data structure is just an unordered set, and these two additions of elements to the set commute with each other. In general, however, we have to carefully design the interface of our data structures to ensure that strong convergence will hold in every execution. For instance, here's a different execution that isn't strongly convergent. Let's say we start with both replicas having the same photo album containing one photo. As before, I add a photo, and we'll again suppose that my photo makes it first to replica 1. Meanwhile, let's say that our photo application offers a share with mom operation that takes a photo as its argument. My partner wants to share all the photos with his mom, so he tries to map the share with mom operation over everything that's in the photo album. This map operation makes it to replica 2 first, and it gets applied to everything in the photo album, which at that point is just one photo. But later on, when the photo that I added arrives, it wasn't part of the set at the time the map operation ran. So according to replica 2, that photo isn't shared with my mother-in-law. Meanwhile, replica 1 receives the map operation second and maps over both photos, so both of the photos get shared there. These operations unfortunately don't commute with each other, and so if this map operation is part of the interface that our photo album provides, then strong convergence won't hold for every execution. A way to fix this is to carefully design the data structure's interface in a way that ensures that all operations on it do commute. Data structures with this behavior are known as conflict-free replicated data types, or CRDTs. They often work by playing clever tricks to make operations commute when they otherwise wouldn't, or leveraging assumptions about the order in which operations are applied. New CRDT designs are an active area of research. As the designs of these data structures get more complex, they motivate the need for mechanically verified implementations that are guaranteed to converge in all possible executions. We'll come back to that later, but before we do, let's look at a different kind of issue. Let's say that, once again, I add a photo to this shared photo album. This time, I happen to communicate with replica R1, and R1 asynchronously sends the update to R2. Meanwhile, my partner comes along to look at the photos. Suppose he sees my update because he happens to talk to the same replica as the one on which the update was made. But let's suppose that he tries to leave a comment after that, and unfortunately that right goes to replica 2, which hasn't gotten the photo yet. Because the photo isn't there yet, the replica can't attach the comment to it. This would probably manifest as some sort of inscrutable error message, like, sorry, something went wrong, try again. And you've probably seen this sort of thing before on web apps that you've used. To see what went wrong here, we have to consider the causality of events. My partner attempted to leave a comment on the photo because he saw the photo in a response from the server, and that happened because of the previous add operation. So the add operation here is part of the causal history of the attempted comment. We can see that by following these messages forward through time and seeing that the comment operation is reachable from the add. But at the time the attempted comment happened, replica 2 had not found out about this add event that's in its causal history yet. So this is a violation of what's known as causal consistency. One way to fix this is to use a mechanism that ensures messages are delivered to replicas in causal order, where the word delivered means actually applied to the replica's state after having been received. A widely used approach is to attach metadata to each message that summarizes the causal history of that message. For example, you could use a vector clock for this. We can use this metadata to determine the causal relationship between messages, if there is one, and delay the delivery of a message to a given replica until every causally preceding message has been delivered. In this case, the comment message to replica 2 would be queued until the add message arrives, and then finally, the comment can be applied. Here again, I'd argue there's a need for mechanically verified implementations, since a causal message ordering abstraction is such a useful building block of distributed systems. But a lot of systems don't get this right, and we'll come back to this later as well. It turns out that even knowing what policy we should enforce is non-trivial, because these consistency policies and the properties that they specify about executions don't necessarily map nicely onto the invariants that we care about for a given application. Let's suppose, for instance, that my partner and I are using the free tier of our photo sharing service, which says that we can have at most 1,000 photos, and otherwise we have to start paying or we risk our old photos being deleted. If we currently have 999 photos in the album, then adding one photo should be fine. The invariant hasn't been violated yet. On the other hand, what if I add the 1,000th photo and my partner also adds a 1,000th photo concurrently? Then, when these two replicas synchronize later, the invariant will be violated. What should we do about this? If the invariant really needs to be maintained, then either my update or my partner's update would need to be rejected, which would require us to synchronize replicas every time we add a photo. In practice, we might want to avoid that synchronization until we get close to the 1,000 photo limit. Furthermore, other operations like deleting a photo wouldn't require the synchronization at all to maintain their invariant. In general, the need for replicas to synchronize will depend on the operation and on the application-specific invariants we need to maintain. Application-agnostic properties that we talked about earlier, like strong convergence and causal message delivery, don't necessarily get us all the way there, but they might get us some of the way. In fact, work on verifying these application-specific properties, like ensuring that this 1,000 photo invariant holds, often rests on assumptions that properties like strong convergence or causal message delivery are already present. And we can simplify this application-specific verification task, or for that matter, just the informal reasoning about the behavior of application code, if we can rely on certain properties being true of the underlying data structures, or underneath that, the messaging layer. So we've just seen a couple examples of policies that we might want to enforce about the consistency of replicated data. Knowing that such a policy will hold for all executions requires reasoning about an often very large state space of executions, with lots of possibilities for message loss and message ordering. The specifications of these policies are called consistency models, and there are a lot of them. I showed this figure to my grad students a while ago, and now it haunts their dreams. It's from a survey paper published in 2016 by Viotti and Vukolich that cataloged over 50 notions of consistency from the distributed systems literature and ordered them by their so-called semantic strength. In other words, the higher up you go in this ordering of consistency models, the fewer executions are allowed, and the less disagreement among replicas is allowed. The lower you go, the more executions are allowed, and the more disagreement among replicas is allowed. And as you can see, it's a partial order. There are many pairs of consistency models for which neither is stronger than the other. Just now, we looked at 2 points in this space. Causal consistency, which we just talked about, is over here. Strong convergence, which we talked about before that, does not appear on Viotti and Vukolich's figure, although they did talk about it in the paper from which this figure came. If it did show up in the figure, then it would have to be a lower bound of both strong eventual consistency over on the right side and causal plus consistency over on the left side. Although strong convergence doesn't appear by itself on the figure, I think it is a nice property to consider independently because it's the safety piece of strong eventual consistency that we do see on the figure. I find this figure to be a little bewildering, not only because this partially ordered set has so many elements, but also because some of the elements of the set are lumping together safety and liveness properties. But if it is bewildering, then that only goes to show that even figuring out how to specify the behavior we want from distributed systems is hard, let alone actually verifying that the specifications are satisfied. So we really have 2 problems. One problem is making precise what policy or combination of policies or parts of a policy that we want for a given application. And another problem is ensuring that no execution violates that policy. These are really hard problems, and programmers shouldn't have to tame this zoo all on their own without help. Programmers ought to have powerful, language-integrated tools for specifying the behavior they want from distributed system implementations and then ensuring that their implementations meet those specifications. So that's the blue sky vision. We want programmers to be able to mechanically specify and verify interesting correctness properties, not just of models, but of real executable implementations of distributed systems. Moreover, they should be able to do this using verification capabilities integrated into the same general purpose, industrial strength programming language that they use for implementation. Many of us are already sold on language integrated verification by means of expressive type systems. And that's the approach to verification that I'm going to be focusing on today. This brings me to the next part of the talk. So we've just talked about distributed systems and some examples of properties that we might want to specify and verify. And now we'll look at liquid Haskell, and we'll turn to how, and indeed whether, we can use liquid Haskell to accomplish what we want. The language-integrated verification approach that's taken by liquid Haskell centers around refinement types. For the purposes of this talk, I'll define refinement types as data types that let programmers specify logical predicates that restrict or refine the set of values that can inhabit the type. Depending on the expressivity of the predicate language, programmers can specify very rich properties using refinement types, sometimes at the expense of decidability of type checking. Liquid types, on which liquid Haskell is based, avoid that problem by restricting the refinement predicates to an SMT decidable logic. Here are a couple of simple examples, which I've written using liquid Haskell syntax. For instance, we can define a type called evenInt that refines Haskell's built-in int type with a refinement predicate, which I've highlighted here, that says our int has to be evenly divisible by 2. Likewise, we could define an oddInt type with a refinement predicate that says that we get a remainder of 1 when dividing by 2. Let's look at how we could use these types. In Liquid Haskell, I could write a function called odd_add that takes two odd ints and returns their sum. The type of the arguments here expresses the preconditions that x and y will be odd, and the return type, evenInt, expresses the postcondition that x plus y will evaluate to an even number. Liquid Haskell automatically proves that such postconditions hold by generating verification conditions that are checked at compile time by an underlying SMT solver. If the solver finds a verification condition to be invalid, type checking will fail. For example, here if the return type of odd_add had been oddInt, then the odd_add function would fail to type check and Liquid Haskell would produce a type error message. None of this is news to people familiar with refinement types, but it's worth pointing out that just with what we've seen so far, we can already do some rather useful things. For example, here's a function called tail from the Haskell prelude, Haskell's standard library, which, given a list, gives everything that comes after the head of that list. But the list had better be non-empty. If you were to call tail on an empty list, you would get an exception at runtime. Using refinement types, we can give tail a type that says that its input cannot be an empty list. If we do this, then we can actually get rid of the empty list case, making our code a little bit simpler. Moreover, we can also add a refinement predicate to the return type of tail that will say something about the length of the list it returns. In particular, this refinement predicate says that the list returned by tail is one shorter than the argument list. Now tail has a postcondition that might be useful to callers of tail. So far, this is pretty much what you would expect from a refinement type system. Where I think Liquid Haskell really shines, though, is where it lets you go beyond this, beyond specifying preconditions and postconditions of individual functions, and lets you verify so-called extrinsic properties that are not specific to any particular function's definition, using a mechanism called refinement reflection. Let's come back to our even and odd example to see what that might look like. Here's a type annotation for a function called SumEven. The type of SumEven expresses the extrinsic property that odd_add returns an even number. In fact, SumEven is a Haskell function that returns a proof that odd_add returns an even number. We see that the return type of SumEven is proof. In Liquid Haskell, this proof type is just a type alias for Haskell's unit type. The refinement predicate that refines proof specifies the property that we want to prove, namely that when we call odd_add, the result will be even. We're able to refer to odd_add in the refinement type of SumEven thanks to Liquid Haskell's refinement reflection mechanism. And we can now write the body of the SumEven function. It ignores its arguments and returns unit. The body of SumEven doesn't look like much, but it is an honest-to-goodness proof term. The reason it doesn't look like much is that this particular proof, the proof that if x and y are odd, then a call to odd_add xy will evaluate to an even number, is one that is easy for the underlying SMT solver to carry out automatically. If that weren't the case, then we would need to write a fancier proof term here using the proof combinators that Liquid Haskell provides. Now, SumEven is not too exciting of a property. After all, it doesn't tell us anything that we didn't already know from the refinement type of odd_add. But now that we have this ability to refer to odd_add in refinement predicates, we can do more interesting things too. For example, I can use Liquid Haskell to prove that odd_add is commutative. This time, the refinement predicate on our return type has two calls to odd_add. So we need a proof that's relating the results of multiple calls. Once again, Liquid Haskell can come up with this proof automatically, and so the body of odd_add com here can still just be unit. Liquid Haskell accomplishes this in part by leveraging the underlying SMT solver's knowledge that addition on ints is commutative. While both of these proofs, SumEven and odd_add com, were automatic, in general, this may not be the case. Liquid Haskell programmers can specify arbitrary extrinsic properties in refinement types, and the programmer can then prove those extrinsic properties by writing programs that inhabit those types using the provided proof combinators. So we see Liquid Haskell can do more than traditional refinement types. It doesn't just let you give more precise types to the programs you were writing anyway. It also lets you use refinement type annotations as a place to specify any decidable property about your code that you might want to prove. And you can then assist the SMT solver in proving that property by writing Haskell programs to inhabit those types. I see Liquid Haskell as sitting at the intersection of SMT-based program verifiers like Daphne and proof assistants that leverage the Curry-Howard correspondence like Calc and Agda. A Liquid Haskell program can consist both of application code like odd-add, which runs at execution time as usual, and verification code like sum-even and odd-add-com, which are only type-checked. But pleasantly, both of them are just Haskell programs, just with refinement types. Being based on Haskell lets programmers gradually port code from plain Haskell to Liquid Haskell, adding richer specifications to code as they go. For instance, a programmer might begin with an implementation of odd-add with the type int, arrow, int, later refine it to oddint, arrow, even int, like we see here, yet later prove the extrinsic properties sum-even and odd-add-com, and still later use the proofs returned by sum-even and odd-add-com as premises to prove another, more interesting extrinsic property. One last thing to note is that unlike with a traditional proof assistant, which would require you to extract an executable implementation from the code that you wrote in the proof assistant's vernacular language, in Liquid Haskell, you're proving things directly about the code you're going to run in Haskell. So at the end, you have immediately executable verified code with no extraction step required, and hence no need to trust the extraction process. So now that we've had a taste of Liquid Haskell, let's get on to the fun part, the adventures. In my group, we've been looking at how to use Liquid Haskell, and in particular, how we can use this nifty refinement reflection and theorem proving capability to express and prove interesting properties of implementations of distributed systems. In particular, we're interested in addressing two of the problems that I discussed in the beginning part of the talk. First, we're interested in making sure that replicated data structures are strongly convergent. And second, we want to guarantee that messages are delivered at replicas in causal order. A third problem I discussed in the first part of the talk is this problem of guaranteeing that application-specific invariants hold. And while I won't be talking about that one specifically, I'll just point out that one of our goals is for the results of these two verification tasks to be usable as modular building blocks in the verification of application-level properties later. So if we're successful with these, hopefully that third task will be easier. So let's start by talking about convergence of replicated data structures. This was joint work with my collaborators Yian Liu, James Parker, Mike Hicks, and Nikki Vazoo, and my PhD student Patrick Redmond. Recall from before that strong convergence means that if replicas have applied the same set of update operations in any order, then they have equivalent state. And data structures that give you this property are called conflict-free replicated data types, or CRDTs for short. Like we saw before, the strong convergence of a replicated data structure depends on the commutativity of the operations on that data structure. This depends on which operations the data structure provides. However, once you have that commutativity proof, the rest of the reasoning to get strong convergence is independent of the specifics of the particular replicated data structure. We were able to leverage this independence by stating and proving the strong convergence property at the level of a generic CRDT interface in Liquid Haskell, and then plugging that together with a data structure-specific commutativity proof for each individual CRDT we wanted to verify. In Haskell, those generic interfaces are called type classes. So being able to do this proof in this modular fashion required extending liquid Haskell to add the ability to state and prove properties at the type class level. This was actually a huge challenge because liquid Haskell operates at an intermediate level of Haskell code after type classes have been compiled away. My collaborators extended liquid Haskell to support type classes, which required an overhaul of liquid Haskell and came with its own interesting challenges, and you can read all about that in our OOPSLA 20 paper. In this talk, I'll be focusing on the second part of the work. Once it was possible to state and prove properties of type classes in liquid Haskell, it meant that an operation-agnostic proof at the CRDT type class level could be combined with an operation-specific commutativity proof at the individual CRDT instance level to get a complete proof of strong convergence for that CRDT and verified executable code. Let's take a closer look at the property that we needed to prove at the type class level and how we expressed it in liquid Haskell. So here's a liquid Haskell type class for CRDTs. Each instance of the type class has an associated op type that specifies the operations that can update the CRDT's state. The apply method takes a state and an operation, runs the given operation, and returns the updated state. The type of law commute specifies the property that operations must commute, and implementers of individual CRDT instances need to provide this commutativity proof. What I'm showing here is a simplified version of the CRDT type class that leaves out some subtlety in our actual implementation. In particular, it's not actually the case that all operations must commute. Instead, there is a notion of compatible operations that is CRDT specific. And it's in fact only these compatible operations that must be commutative, because the design of the CRDT would rule out incompatible operations from being applied concurrently. Furthermore, some operations can only be applied when the CRDT is in a given state. For the simplest CRDTs, like a counter, all operations would be compatible with each other and are always applicable, whereas for more sophisticated CRDTs, this isn't the case. And you can find more details on this notion of compatibility in our paper. Once we were able to define the CRDT type class this way, we were able to express a strong convergence property at the level of the type class. Here is the statement of the strong convergence property in liquid Haskell. This is again somewhat simplified from the real thing, but it captures the key idea, which is that if two lists of operations are permutations of one another, then applying either one of those lists to the same input CRDT state will produce the same output state. The proof of this property is about 300 lines of liquid Haskell code. It's by induction over the operation lists, and it makes use of the operation commutativity proof, law commute, supplied by CRDT instances. However, the strong convergence proof itself is independent of any particular CRDT instance and thus applies to all of them. Earlier, I made a distinction between application code and verification code, and we can see that here as well. The apply function is actually used at runtime in the implementation of CRDTs. The law commute function and the strong convergence function never run at runtime. They're verification code. But we can see from the refinement type of law commute that it's a proof about the behavior of apply. And it's because of liquid Haskell's refinement reflection that it's possible to refer to apply in law commute's type. Finally, law commute is called as a function, or in other words, used as a lemma, in the body of the strong convergence proof, which again isn't shown here because it's too long. Now, how easy is it for CRDT instances to supply this operation commutativity proof, law commute? It depends quite a bit on the complexity of the CRDT. Here are a couple of examples. One of the simplest CRDTs is a counter that can only grow. Operations on this counter are just numbers, and the state of the CRDT is their sum. For this CRDT, liquid Haskell can carry out the commutativity proof automatically, just like it could for the proof that addition is commutative that I showed a while ago. So that's one that's easy. On the other hand, here's a fancier CRDT. a dictionary that supports insert, update, and delete operations on key value pairs, and where the values in those key value pairs themselves are of CRDT type. For this CRDT, the commutativity proof took over 1,000 lines of code. Complexity in the commutativity proofs is the result of complexity in the CRDT's implementation, in part. For instance, for this dictionary CRDT, I've elided the implementation of the apply function, but it's a bit hairy. For example, if it receives update operations for a key that has not been inserted yet at a given replica, it'll store those update operations in a buffer of pending operations at that replica, and then will apply them as soon as the relevant insertion happens. It's worth pointing out that this implementation complexity is necessary because these CRDTs are designed in a way that requires very little in terms of ordering guarantees from the underlying messaging layer. That's why it's possible for a replica to receive update operations for a key that hasn't yet reached that replica. While this does mean that we can potentially use our CRDTs in more settings and have a smaller trusted computing base, it makes for a more strenuous verification effort for non-trivial CRDTs. I'll also say that although we already have some modularity in the way that we separate our CRDT agnostic strong convergence proof from the CRDT specific commutativity proofs, this strenuous verification effort suggests that an even more modular approach that separates lower level message delivery concerns from higher level data structure semantics is really what is called for. And that idea will lead me into the second and final project that I'll discuss in this talk. Let's recap the example that we saw earlier to motivate the need for causal message delivery. In this example, I updated a shared photo album with a new photo, and my partner saw it, but when he tried to leave a comment on the new photo, he communicated with a replica that hadn't gotten the update yet. And as we discussed, this is a violation of causal order of messages. His comment causally depended on my previous photo add operation. One way to solve this kind of problem is to have replicas keep track of metadata representing how many messages they've delivered from each other, and for messages to carry metadata representing their causal dependencies and not deliver a message at a replica until its dependencies have been satisfied. For instance, here the response from replica 1 to my partner could carry metadata that indicates that replica 1 is aware of one message delivery, and this metadata could be threaded through in the next request from my partner. And when that request arrived at replica 2 could check the causal metadata, compare it to its own metadata, determine if the message is deliverable, and if necessary, queue the message until the causally preceding message has been received and delivered. And this is the foundation of causal delivery. A classic protocol for ensuring causal message delivery in the case of broadcast messages is known as the CBcast protocol, short for Causal Broadcast. This protocol was introduced by Ken Berman and his collaborators in the early 90s in the context of their ISIS system for fault-tolerant distributed computing. The CBcast protocol ensures that when a process receives a message, that message is delayed if necessary, and then delivered, meaning applied to that process's state, only after any causally preceding messages have been delivered. In particular, as we see from this excerpt from the CBcast paper, if the send of message M happens before the send of message M prime, in the sense of Lamport's happens before relation, then we know that on all processes, the delivery of M has to precede the delivery of M prime. In CBcast, this is done by using vector clocks to represent causal dependencies, delaying messages in a queue on the receiver's side until it's okay to deliver them, and doing a deliverability check by comparing a receiving process's vector clock with the vector clock of the message. In our recent work, my students and I have implemented Berman et al.'s CBcast protocol in Liquid Haskell, and we've used Liquid Haskell to verify that a causal delivery property holds of our implementation. Here's a simplified look at how we can use refinements in Liquid Haskell to express the type of a process that observes causal delivery. A process keeps track of the events that have occurred on it so far, including any messages it's delivered. And that sequence of events comprises its process history, or phist in the code here. This type causal delivery says that if any two messages, m and m prime, both appear in a process history as having been delivered, and m causally precedes m prime, then those deliveries have to appear in the process history in an order that's consistent with their causal order. So this is essentially taking the definition of causal delivery from Berman et al.'s paper and turning it into a property that we can enforce about a process. Now that we've defined this causal delivery type, the verification task before us is to ensure that for any process history that could actually be produced by a run of the CBcast protocol, this causal delivery property actually holds. The way that we accomplish this is to express the CBcast protocol in terms of a state transition system, where states are the states of processes and state transitions are the operations that broadcast, receive, or deliver messages. Here we have an op type that represents those three kinds of state transitions, receive, deliver, and broadcast, and a step function, which I've just shown the type signature of here, which takes us from process state to process state. We can then prove a property that here I've called causal delivery preservation. It says that if a process observes causal delivery to begin with, then any process that could result from a sequence of state transitions produced by the CBcast protocol will observe causal delivery too. This took a few hundred lines of liquid Haskell code to prove, with the most interesting part, of course, being the part that dealt with deliver operations. I think there are a couple of interesting things to point out about this result. First of all, we found that the real key was implementing the protocol in terms of a state transition system. This wasn't the way it was described in the original paper, although of course all the ideas were there, but we found that that's what we had to do to be able to express and prove properties like this causal delivery preservation property. And it took a while for us to arrive at that design, even though it seems obvious in retrospect. Second, I want to note that this protocol is entirely agnostic to the content of messages. It only looks at the causal metadata attached to messages, specifically vector clocks, not the messages themselves. Now, there are downsides to this choice. If you're implementing an end-to-end system, then you might be able to make smarter choices about message delivery if you know something about the semantics of the messages you're dealing with. A message that might be deemed undeliverable by this agnostic causal broadcast protocol might be deliverable faster under your custom semantics. On the other hand, choosing to be agnostic to message contents means that we now have a general, verified causal message broadcast library that can sit at the foundation of many applications. We're coming close to the end of my talk, but if I'm going to talk about causal broadcast as being foundational, then I can't help but show this wonderful image, which I can't take credit for. This was created by Matt Wiedner, who's currently a PhD student at CMU. And the idea here is that once basic needs are covered, food, water, shelter, and then internet, then causal broadcast sits just above that as a foundation for things like CRDTs, and therefore collaborative software. Now, I mentioned earlier that some of our CRDTs took strenuous proof effort to verify. And part of the reason for that is because those CRDTs did, in fact, not make an assumption of causal message delivery from the underlying network. However, now that we do have this new work on verified causal broadcast, my claim is that it will be easier to carry out those CRDT commutativity proofs, and I'd like to go back and revisit that work and build on top of causal broadcast. Conversely, some CRDTs don't actually need causal broadcast to be strongly convergent, like, for instance, the counter CRDT that I showed earlier. In fact, my claim is that the CRDTs that don't need causal broadcast are exactly the ones that Liquid Haskell could verify the commutativity of automatically. For the ones that do need causal broadcast, the verification task, not to mention the implementation of the CRDTs themselves, ought to get simpler now that we have causal broadcast to build on top of. I also want to add that CRDTs are not the only thing that can sit at this middle level of this hierarchy. Once you have causal broadcast, it also becomes relatively straightforward to implement, for example, a causally consistent database. There's already been a lot of nice work from the PL community on verification of causal consistency, but as far as I'm aware, that work doesn't factor out causal broadcast into its own separately verified layer, which is what we've done. So we think that it ought to be possible to verify causal consistency in a modular way on top of causal broadcast, and perhaps simplify the verification effort. And that's one of the things that we want to look at next. As I wrap up this talk, I want to come back to this blue sky vision that I mentioned earlier, that programmers should be able to mechanically express and prove rich correctness properties of executable implementations of distributed systems, using the same industrial strength language that they use for the implementations themselves. Are we there yet? Our results so far suggest that with Liquid Haskell, it is possible. Unfortunately, I think it's still way too hard to do. Thanks to refinement reflection, Liquid Haskell can be used to turn Haskell into a proof assistant. And make no mistake, I think it's great that this is possible at all. But developing long proofs in Liquid Haskell can be quite painful. Part of the problem is that more established proof assistants, like Agda and Coq, offer much better support for interactive proof development and insight into the proof state while a proof is ongoing. For instance, what subgoals still need to be proved to finish a partially complete proof. In contrast, Liquid Haskell provides only very coarse-grained feedback to the programmer. Either it reports a type error, which means that your proof isn't done yet, or it doesn't report a type error, which means that your proof is done. My students and collaborators and I have been thinking about how to improve the situation, and one of our proposals is to extend Liquid Haskell with support for Agda-style typed holes and interactive editing commands that take advantage of them. Typed holes would allow programmers to indicate unfinished parts of a proof and incrementally complete the proof in a dialogue with the compiler. GHC Haskell, in fact, already has its own support for typed holes, which was itself inspired by Agda. But we think that typed holes would be especially powerful and useful if combined with Liquid Haskell's refinement types and SMT automation. We published a short paper about this idea at the Hatra workshop last year, but there's still a lot of work to do. So I would invite collaboration from anyone who's interested in helping out here. To conclude, we saw that we can use Liquid Haskell's refinement types to express properties about the convergence of replicated data structures. And we can use Liquid Haskell's refinement reflection and proof combinators to prove those properties extrinsically. Likewise, we can express and prove properties about the order in which broadcasted messages are delivered at a process. In particular, we can prove that messages are delivered in causal order. And this should enable easier implementation and verification of applications on top of the message layer, whether it's CRDTs or anything else. And we find that while Liquid Haskell is up to the task of these verification projects, we still think it could be a lot easier to use, and we look forward to continuing to improve it. To learn more about our work, you can find my colleagues in my research group's website at lsd.ucsc.edu, and my blog, where I sometimes discuss research, is at composition.al. I look forward to answering your questions in the Q&A, and thank you for listening.